All right, the next property of electricity to talk about is electrical resistance. So, unlike what the Borg said, resistance isn't futile. Resistance is just a property. So, resistance is just describing how well a wire, a covering, whatever it is resisting the passage of electric current. This can describe the actual wire that the electricity is moving through or the insulator that's around it. So think about like copper versus rubber. Which one is going to have more electrical resistance? And the rubber should have more electrical resistance because it's an insulator and it's got those tightly bound electrons. It's not going to allow the flow of the electrons like the copper would. Okay, so the material makes a big difference. So resistance is the ratio between potential difference or voltage and current or the amps. And it has its own unit. It is represented by R, big R, and its unit is ohms. So you can see the O in Greek. So let's take a look at what electric resistance is as far as that relationship with voltage and current. You saw real quick that I flipped over here. So this is Ohm's law, and it's just the relationship between current, voltage, and electrical resistance. So these are the three of them together. So resistance is equal to voltage divided by current. And so that's just basically the relationship. You can rewrite it, as you can see I've written it here. Current is equal to voltage divided by resistance. The way you write the formula all really depends on which of the elements you have in a problem. So what if the voltage is doubled? What will happen to the current? So let's take a look. Let's see if let's grab a pen. So let's say we have a voltage of 120, because that's a standard voltage, and we have a resistance of 10. Right? So 120 divided by 10 is going to get you a current of 12 amps. But if we double the voltage, so 240, and the resistance stays the same at 10, what's going to happen to the current? Is the current going to go up or down? It should go down, and it will go down by, or no, it will go up by how much? It'll double, because 240 divided by 10 is 24. Okay. And what if the resistance is doubled, what happens to the current? So let's grab the eraser. We use the same problem. Oh, I meant to leave the 10. So 120 divided by 10 is still going to get us our 12. But if we double the resistance, so 120 divided by 20 is going to do what to the current? Now it's going to go down. I was getting them reversed. And so now we're going to get a current of 6 because we've doubled the resistance. It's going to slow the current down. Okay. All right, so a couple of problems. So a light bulb in a 120 volt circuit is switched on and a current of 0.5 amps flows through the filament, what is the resistance of the bulb? And a second problem, what current would flow through an electrical device in a circuit with a potential difference of 120 volts and a resistance of 30 ohms? You can work on these problems on your own, and I will post a video with the solutions like I did in the heat chapter that I will work through to show you how to get the answers. All right, so I want to talk a little bit more about electrical resistance. This information is not specifically in your text, but I think these are important things for you guys to understand. So the electrical resistance is actually determined by 4 different variables. So one is material type, and that one should make sense, right? The material type, whether it's a conductor or an insulator, is going to make a difference on how the electricity is going to flow. So it's going to flow better if it's in a conductor than it will if it's in an insulator. The next thing that's going to change the electrical resistance is the length. So the length, the longer the wire, the more resistance you're going to get. And that should make sense because the longer those electrons have to travel, the more places they have to bump into and slow down. And so that's going to create more and more resistance. It'll slow down the current. The next thing that's going to affect the electrical resistance is the diameter. How big around is the wire? So if the wire is thick, there's going to be less resistance. I know that sounds weird, but think of it this way. If the wire is super, super thin, super tiny, there's not as much space to jam those electrons in. But if it's big, then a lot of electrons can flow through there, and it allows a lot of current to be able to go. So the bigger the wire, the less resistance you get. The smaller the wire, the more resistance you get. And then the last one is temperature. The temperature of the material makes a difference. Most materials have increased resistance with increased temperature. And this has to do with the molecules. Remember, as you increase the temperature in molecules, it increases their kinetic energy. They move around more. And so the material, the atoms in the material are moving around more, and it gives more things to have the electrons run into and bump into as they're trying to make it down the wire. And so they're having to kind of bump into and dodge things as they run through the wire. So it makes it more difficult for the current to run if the wire is hotter. If it's cooler, it will work better, and that's actually why they've been working on supercooling different wires for electricity transfer. So got this little video to show you that's related to this. And I'll let him talk you through it.
In this video, I will explain electrical resistance. Resistance can...
I'm going to fast forward because we just talked about some of this. There we go. That's what I wanted to show you, his marble experiment.
marbles, which flow along the length of a wire, demonstrated by the Jenga blocks. Energy is provided by elevating the table, or a battery supplying a voltage to a circuit. When energy is supplied, the electrons flow through the wire. This flow of electrons is current. It took just over 6 seconds for some number of electrons to pass a point. This is an arbitrary value of time, but it is representative of how much current is flowing, since current is how many electrons pass a point in a certain time. A longer time means a smaller current. Therefore, any resistance to the flow of electrons will decrease the current, demonstrated by an increase in time. The next thing to consider then is what determines the amount of resistance. It can be determined experimentally that resistance is equal to the resistivity times the length, all divided by the area.
You do not need to worry about that formula. I'm not going to ask you anything about that.
Where resistivity is a material-specific value. So according to this equation, increasing either the resistivity or length will increase resistance, whereas increasing the cross-sectional area will decrease resistance. Let's test this. We have increased the wire's resistivity by adding in obstructions, just like a material's lattice structure. The electrons collide with these obstructions, impeding their flow. This time, they took 11 seconds to pass through the wire. We have decreased the current by increasing resistance. Now, let's increase the area of the wire. This only took 3 seconds. The electrons have more room to move. Increasing the length of the wire simply means the electrons will collide with more obstructions. You can see here that the electrons at the back had to pass by 2 obstructions to reach the end, whereas the electrons at the front flowed through unobstructed. A resistor can be considered to be a wire with a known amount of resistance. Here, we have reduced the width of the wire in one spot, representing the presence of a resistor. The electrons took 11 seconds again, and you could see where the flow